Okay, the fourth video in this series about logarithmic differentiation, and now I'm going to show you a different method where there is no logs at all in your problem. So there's some steps I want you to follow here, so let's write the steps down first. One is you have to recognize that you have a very complex derivative, and there is no log or natural log present. And in all honesty, guys, I would tell you if I want you to do logarithmic differentiation if there's no log in the problem, okay? So it's not like you're going to have to worry about that. I will tell you, okay? The technique is you're going to natural log both sides of your equations, okay, and use logarithmic rules to expand your problem. Now the one thing I want you to note, this is not doing the derivative. Okay? This is just expanding your problem with log rules. Okay? So I'm making a big deal here that this is not the derivative. Then you're going to take the derivative of both sides. After you do that, take the derivative of both sides of your equation, and we're going to use dy dx, which is the same as y prime, but we're going to use dy dx, and then we're going to solve for dy dx and replace the y with the original function. Now, don't worry if this doesn't make sense quite yet. We're going to do some examples so you know exactly what I mean. Okay? So here I have this problem here, and I want you to look at this. If we were doing this from before, we'd notice that, oh, we have a quotient rule here, and then when I did my f and then my g, when I did the top part, I would have the numerator, I would have to have the product rule inside the quotient rule, which is doable, but it's quite a bit of work. So what we're going to do is to do a different technique. This is called logarithmic differentiation, where we're going to actually log both sides, even though notice there's not a log here at all, and then use those rules to expand it to take the derivative an easier way. Because you know the derivative, if y equals a natural log of u, y prime is 1 over u times u prime, which is probably one of the easiest derivatives there are. So, first of all, I'm going to natural log both sides of these. So if I natural log both sides, the left is going to be natural log of y equals, and then I have the natural log. Now, inside this parentheses, if you will, I've got these multiplied so I can pull it apart with addition, and this I can subtract it. So I can actually say it's a natural log of x squared plus 1 plus the natural log of x plus 3, I should put parentheses around this, x plus 3 to the half minus the natural log of x minus 1. Now, once I natural log both sides, this is one of the natural log rules that you can use where you can pull it apart with addition and subtraction if I have multiplication and division. Then the last log rule is right here. We're going to bring this exponent down front, so I have sufficiently expanded this as far as it can go, plus 1/2 natural log of x plus 3 equals the natural log of x minus 1. Oops, sorry, not equals. Sorry, minus the natural log of x minus 1. So basically, all I've done is expand that problem. Now I'm going to actually take the derivative. So this is the part I want you to make sure that you notice. So I'm going to change this to red just so you can see that this is actually the derivative now. So when I do the derivative here, the derivative of natural log is 1 over y. And since this is the derivative of y with respect to x, we're going to say dy dx. So you need to say that I'm taking the derivative, and it's the derivative of y with respect to x. You could say y prime there, but we're going to use this. Now we're going to take the derivative over here. So the derivative right here is 1 over x squared plus 1 times the derivative of the inside, which is 2x. So I'm going to do it all at once. So this is 2x. Well, let's do it in steps here so that I won't confuse you. So this is 1 over x squared plus 1 times the derivative of the inside, or 2x, plus 1/2 times 1 over x plus 3, because that's the derivative of that, minus 1 over x minus 1. So here's the first time we did the derivative. Now I'm just going to rewrite this so it doesn't look quite so bad. So I have 1 over y dy dx equals 2x over x squared plus 1 plus 1 over 2 times x plus 3 minus 1 over x minus 1. Which I don't know about you, but this is easier than if we had to do product and quotient. Now, we have to solve for dy dx. So this is what we're actually going to solve for right here, okay? So if we're going to solve for that, what I have to do is, if you look at both sides of the equation, I'm going to go back to black again here, is that we're going to multiply both sides of the equation by y. Because then this will make it solve for dy dx equals, and then we have y times this whole, these three fractions, okay. Now this is not wrong, but you want to replace that y. So what we're going to do, this is a 1 if it lets me write it, there we go. So we're going to replace this y, and we're going to go back up and we're going to replace it, because doesn't y equal this whole thing here? So you're basically going to replace the y with this right in that spot here. So the actual derivative is going to be, ready, x squared plus 1, x plus 3 to the half, divided by x minus 1, times 2x over x squared plus 1, plus 1 over 2 times x plus 3, minus 1 over x minus 1. And that is the answer. Now, I never said it was beautiful, but this is the derivative. It's a lot easier to do, and that's your answer. Now, the one thing I do want to caution you is sometimes they'll look for a common denominator here if it's a decent way to do it. This one we're not going to. I just want you to see how you do the method. All right? So let's try another one. Okay, so I have y equals this radical. So if I had to do this, I'd have to do the power rule, then quotient rule. So we're going to do logarithmic differentiation. So I'm going to actually, we're going to change this to a half. So everything gets raised to a half. So this would be 1 all over t to the half, t plus 1 to the half. So all I did was power to the power. Okay, so if we were going to pull this apart, okay, we would have the natural log. So we'd have this, we're going to natural log both sides now. All right, so when I do that, okay, I'm going to have the natural log of y equals the natural log of 1 minus, now be careful, it's going to be the natural log of t to the 1/2, okay, all right, minus the natural log of t plus 1 to the 1/2, okay. And if you have this negative here, because you're excuse me, this should be a plus, I apologize, I'm thinking ahead. So you have natural log of 1, and then these two are hooked by multiplication, so there's a plus. But what I was thinking ahead is I've got to change the sign of that when I get done. So this is going to be the natural log of y, okay, is going to equal the natural log of 1 minus a half natural log of t, okay, minus the half natural log of t plus 1. Okay, now we can start doing the derivative. Okay, this is where we're starting the derivative. I just want you to notice this. I'm going to change this to red so that you notice all we did is expand it. So I'm going to call this 1 over y, and then I have to say this is derivative of y with respect to x, equals, well, the natural log of 1 is 0, so the derivative of a constant would be 0 anyway, so this isn't going to show at all. Okay, so then this is going to be negative a half times 1 over t minus a half times 1 over t plus 1, and the derivative of the inside is going to be 1. So now I have 1 over y dy dx equals negative 1 over 2t minus 1 over 2 times t plus 1. Okay. Now we are going to, I'm going to change this back to black. We're going to actually solve for dy dx. So I'm going to multiply both sides by y. So I have dy dx equals y times this. And then we go back up here and replace this y with our original equation. Don't use anything you did, we'll replace it there. So it's going to equal, dy dx is going to equal 1 over t times t plus 1, and then it's going to be multiplied by negative 1 over 2t minus 1 over 2 times t plus 1. And there is our derivative. Okay? I'm going to do a couple more problems, but I'm going to stop this video right here and can do some more problems.